All right, so today we're going to be looking at electric fields. Really, one of the things that we know about electric charge is they exert forces on things. Like when we talk about uh, like charges repelling each other, really they're pushing away from each other. That's a force between them. Forces are pushes or pulls. Or if I'm looking at oppositely charged objects, they pull towards each other. Like when you rub a balloon on your hair, stick it next to the wall, the charges of the wall and the balloon pull towards each other, and the balloon, can stick to the wall. There's enough of a pull there. So today we're looking at well, we know that attraction doesn't have to be touching. Like after I rub the balloon on my hair, if I put it next to somebody with longer hair, we can see the hair gets pulled towards the balloon from a distance. The force is being exerted without the balloon coming into contact with the hair. Well, you can see the same thing with Scotch tape. If you lay like on a table two pieces of Scotch tape, one on top of the other, and then you take them off of the table and then pull them apart, you can actually see the Scotch tape kind of pulling on each other without touching. And so we have this force that's being exerted at a distance. We would say that force exists as a field. So in this case, we're talking about an electric force. We have an electric field. So really the what it allows us to do is if we know the electric field and we know a charge being placed into that electric field, we can figure out the force being exerted on that charge. So then you might be asking, well, how do I find the electric field? Well, to find the electric field, we're still using Coulomb's constant there. We're just taking it times the charge emitting that electric field and dividing it by r squared. How far away from that charge are we, but squared. Taking it all together, this should look pretty familiar. Like if I substitute this in for E, I would get that the force electric is equal to, I'm going to call that Q1 and I'm going to call that Q2, okay? So I've got Q1 times Kc, should be a 1 there, times Q2 over r squared. Now if I do a little bit of rearranging, multiplication allows me to mix things around. If I put Q1 right there, I get Kc Q1 Q2 all over r squared. All right, and that's the equation that we worked with last time. That just gives us electric force, okay? So now we're really going to focus in on finding the electric field and finding the force of a charge placed in an electric field, all right? But for this video, this is going to be the key thing we're looking at as I completely destroy my setting there. All right, so taking a look at that, down here at the bottom, I have my first question. So a charge, let's see, is that my first question? Yes, it is. A charge of Q that's equal to negative 3.1, that should be microcoulombs. I'm just going to put a U there for now. Just know that's my cheap way of doing a micro symbol. Negative 3.1 microcoulombs produces an electric field of magnitude 0.78 times 10 to the fourth newtons per coulomb at a distance r from the charge. And they want us to find r. So in this case, I know the electric field or how strong the electric field is. Okay, so in this case, I'm looking for r squared. I would start off to solve this one by looking at algebraically getting r squared by itself. So E equals Kc Q. I actually don't even need to make it Q2 in this case. We're only working with Q over r squared. All right. Multiply both sides by r squared. R squared times the electric field equals Kc Q. Divide both sides by the electric field. And I should get r squared equals that, but let's not do r squared. Pretend that's square root sign. Kc Q all over the electric field. All right. So I've gone through, I've figured out what I'm going to have to type in to figure out how to solve that number 1. So let's even go through and let's plug in our numbers. So r is equal to the square root. Coulomb's constant is still 8.99 times 10 raised to the 9th newtons meter squared per coulomb squared. Keep that going over. That's times the charge that I'm working with. So in this case, microcoulombs. I think I might have mixed this up in the last episode, but uh, Q is equal to negative 3.1 microcoulombs, or negative 3.1 times 10 raised to the negative 6 coulombs. And since my coulombs constant is in coulombs, I've got to convert my charge over to coulombs as well. So negative 3.1 times 10 to the negative 6 coulombs. And we said that's over the electric field, and in that question, it gives us the electric field of 0.78 times 10 to the fourth newtons per coulomb. All right, so now I've got uh, coulombs divided by coulombs, that's coulomb squared, which will be canceled out by that. So my coulombs are gone. Uh, let's see. Newtons here, newtons there, newtons are canceled. So I'm left with meter squared. I know I've got everything set up right. All right, so now let's go ahead and let's actually plug this in. So calculator over. Let's go square root. Let's go. Oh, I hope that's working. 8.99 times 10 raised to the ninth, close parentheses, times open parentheses, 3.1 negative times 10 raised to the 6 negative, close parentheses, divided by, oh, I even forgot a parentheses there. That's done now. Parentheses 0.78 times 10 raised to the fourth, close parentheses, equals, but I'm pretty sure I have to take the square root of that. Let's see. Why is that? Oh, all right. Can't square root a negative. All right. So really, though, the R then, it should be plus or minus here. So really, we're just getting let's even do the square root of 3.57. And, okay. Square root 3.57. Now let's do square root equals 1.89. Sounds about right. And keep in mind that was meters there. So when you do this, just keep that in mind with your signs is you can't really square root a negative because you always have to take out the square root of -1, and that's imaginary. So just know, just if you're looking for R, just make your Q positive. I think is the easiest way to go about that. So yeah, so that's really all we did. We just algebraically solved for R, avoiding that whole negative issue. Really what this means though is, let's look at it a different way. So now we're going to go through some, typically you're also going to be asked to kind of diagram these electric fields and stuff. So two things we can do is, number one, when we do this, typically we're going to make positives red. Positive charges are going to be red. Negative charges are going to be black. That's just the scheme that they use. Because I think at the beginning they actually thought the positive side of a battery was where the electrons were coming from. So they just kind of said that's red, positive's red, and it's stuck forever. All right. So really what we have here is we have this negative charge. All right. And we know that the charge on is negative 3.1 microcoulombs. But what's going on is we have a couple of things. Is the electric field, we say, goes from, like let's say that actually had a positive charge right here. We would be drawing in the electric fields as saying that they're going from the positive charge to the negative charge. And in fact, we would have these lines going, connecting these two things. We could even go like that, depending upon how strong we're talking about. All right. But then we're going to have an electric field coming away from my positive charge, kind of going that way. That means we also have some electric fields coming into my negative charge from the other direction as well. All right. The big thing though is when we're drawing these lines, essentially you draw them away from the positives and towards the negatives. The other things that we need to know about, like when we diagram these electric fields, is the closer together or the more lines we have coming out of a charge, essentially the stronger that charge is. So essentially we could be looking at, let's look at two negative charges. Like let's say we can go 1 and 2, and let's even say that 1 has a charge uh, of -1 coulomb, and let's say Q2 has a charge of -3 coulombs. If I have, like we kind of know, like these things are going to essentially push away from each other, or essentially they're pulling lines to them kind of from opposite ways. That was kind of bad. All right, so now we got 1, 2, 3, 4, 5, 6. I got 6 lines going into Q1, which has a charge of -1c. I would need 3 times that number, so I would need like 18. So 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. You get the point though. Like, let's just do 2 more, I guess, since I'm right here. All right, so the more lines you have coming out of a charge, the stronger that charge is. And keep in mind, this is all kind of relativistic. You know, this isn't solid set in stone rules. Like a charge in -3 should have 18 lines coming into it. Like that's not a rule. It's more of a when you're comparing two different charges. And things get really crazy when we start looking at where are electric fields strongest. Like coming back to the positive and negative diagram here. Oh, you can't see my mouse. That's cool. Like the electric field here is pretty low compared to like the electric fields like right here. Okay, because here it looks like there's kind of a gap. Whereas anywhere in here, it looks like anywhere in here, you know, these lines are really close together. So we know the electric field's stronger there than it is right up there. Simply because where we have more lines closer together, stronger electric field. All right. So I think I'm done rambling here for a little bit. All right. So let's look at one more one more example. All right. So we've got, oh, helps if we can read get that place a little bit better. All right. So we have two charges of -5 are placed. Once again, that should be microcoulombs. Otherwise, our answer is going to be huge. All right, so microcoulombs are placed on a grid. The first is placed at y equals 0.75 meters. The second at x equals 0.75 meters. And we want to find the magnitude of the total electric field at the origin due to the two charges. So really what we're looking at is, so if I go there, and if I go, oh, let's go like 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. All right. So at this point right here, we've got a negative charge, and I'm going to put that Q1. And if I go 1, 2, 3, 4, 5, 6, I'm sure I miscounted, but that's all right. If I put another negative charge over there, call that 2. Really what we're looking at is I want to know what's the electric field at this point right here. And I have a distance. I know that that is It's 0.75 meters away from that charge up there, and it's 0.75 meters away from this charge right there. Luckily, they both have the same charge. It just makes my math a little bit easier to do. And I know that I have these kind of electric fields. So if it's negative, I know like the electric field line going to that one there is going straight up, okay? And I know that the electric field to this negative charge over here, electric field lines go towards them, goes that way, all right? And now if I just do some pretty basic vector analysis, I've got a charge, got electric field to force going that way, electric field going that way. I know that my total electric field is going to be in that direction there. I just need to figure out the magnitude, which that's not drawn to scale. And really, and that makes sense because like at this point here, since I know the field lines here are kind of repelling each other, I know that I'm going to have essentially something that's kind of like this, especially since they're equal charge, and we can even try to go like that and like that. We know that these field lines here are adding together to go into that direction. The big question is what's the strength of that electric field? Essentially, when these electric fields are combined, what is this total magnitude here? All right, so I'm going back to this right here. And I know that I'm using E equals KC Q over R squared. All right. Big thing though is we can say that Q1 we're going to say is going to give us the electric field in the y direction. Q2 is going to give us the electric field in the x direction. You still break things up into the x and y direction. So you're still going to be using some of your trig functions. You're going to be using Pythagorean theorem. That stuff does not ever go away pretty much. All right, so now I need to find Q1. I'm looking for the electric field in the y direction. That'll be equal to 8.99 times 10 to the ninth newtons meters squared per coulomb squared. And I'm going to take that times Q, which is -5 times 10 to the -6 coulombs. I'm sorry about kind of ignoring significant figures there. 0.75 meters squared. All right, so now I'm going to be left with newtons per coulomb, which is fine. That's the unit for electric field here. So let me actually get the calculator back out. All right, 8.99 times 10 to the ninth times 5 negative times 10 xy 6 negative divided by 0.75 squared. All right, and this one I just kind of know I don't need to worry about the parentheses too much here. So it looks like I end up with negative 79,911. And keep in mind that's newtons per coulombs because meter squared, meter squared. And that does seem really high, actually. That gives me 10 to the third. That should have made it smaller. Let me double check I type stuff in right. Not that. All right, 8.99 times 10 to the ninth times -5 times 10 to the -6 divided by let's try it one more time. Okay, 8.99 times 10 ninth times 5 times 10 raised to the 6 negative divided by 0.75 squared. Yep. All right. So that's what I get. All right. So that's the force of the magnitude in the y direction. So now if I go through and I figure out the electric field here, this is going to be the exact same thing. 79,911 newtons per coulomb. But now, so that's in the x direction, or sorry, this is in the y direction, that's in the x direction. So I've got, I'm going to cheat a little bit. I've got negative 80,000 in that direction, negative 80. I rounded it just to make it easy, okay? I need to figure out what this is, okay? What's my total electric field here? So essentially, this is just going to be Pythagorean theorem. So the electric field total is going to equal the square root of negative 79,911 newtons per coulomb squared plus negative 79,911 newtons per coulomb squared. All right. So this math is going to get me to the right answer. Okay, yep, messed up. Let's go with 79,911 squared, and I'm not going to bother like putting the negative in. I know a negative times a negative is a negative. Actually, I could just take that times 2 equals square root. I get a total answer of 226,000. That doesn't seem right. All right. So I get 226,000. That doesn't seem right to me. 22 newtons per coulomb. Try this one more time. Actually, I'm going to use a different calculator. I think that'll just be easier. If you're questioning your calculator, I think it's easier, just try a different one. Hold on for just 1 second. Okay. Almost ready. All right, so we've got square root of 79,911 squared plus 79,911 squared, close parentheses, equals. All right, this sounds much better. So now the answer I'm getting using a good calculator, one, not saying that the one built into Windows is bad, but it's not the easiest to lose. I get 113,011. Really 113,000, probably close enough, and that's newtons per coulomb. So that's the total electric field strength we find at this point right here. And it's being pulled kind of up into this angled direction simply because of the way that the electric field lines are kind of drawn. All right. So a lot of work, a lot of bumbling around, I know. But that's essentially how electric fields worked. Allows us to calculate the electric fields. We can figure out the forces on a charge placed in an electric field. That's the other part. So kind of going back to, if I can go to the right image, come back here, finding the electric force on it. Now that we know the electric field, if I come back and if I place like a known charge, a positive charge here, I know what direction the electric force is going to be in because of that. Anyway, that's a long enough video. Good luck with the practice.